Welcome dear students, welcome to today's online class. Today we discuss one important property of solid, that is electrical conductivity. The importance of electrical conductivity is that it is the property which shows such a variable range of magnitude. That means we know that solids are of two types based on electrical conductivity, three types: conductor, semiconductor and insulator. So the electrical conductivity is as high as 10 raised to 7 ohm inverse meter inverse for conductors, good conductors, and it is as small as 10 raised to minus 20 ohm inverse centimeter inverse for insulator or non-conductors, and semiconductors fall in between. We are interested in semiconductors in this module. We will go to the types of semiconductors in detail. The discussion is based on what is known as band theory of solids or band model, which derives from molecular orbital theory. So what is band model of solids? If you take for example lithium atom, metal atom, you know the configuration of lithium is 1s2, 2s1. So if you take the valence orbital, it is 2s1, so there is one electron in 2s. I am showing this 2s1 here. This is the case of a lithium atom, an individual atom. In the case of a lithium molecule, when two atoms join, according to molecular orbital theory, AOs, atomic orbitals, combine to form molecular orbitals. So in the case of Li2, that means a diatomic molecule of lithium, there will be combination of 2s orbitals forming sigma 2s and sigma star 2s, or there will be two orbitals, molecular orbitals, sigma 2s and sigma star 2s, and there will be two electrons filled in sigma 2s, right? In the case of a solid, we know that it is aggregation of so many atoms, close packing of atoms. So the atomic orbital of one atom is influenced by so many atomic orbitals of all atoms around it. So many AOs will be there to combine and forming many MOs. So naturally what happens, see in the case of Li3, if you suppose, it will be something like this. When we go to Lin, that means many atoms joined, it will be that all the MOs are very close and it forms almost like a band, right? So atomic orbitals of many atoms combine to form closely spaced molecular orbitals which appear like a band, a continuous band. Naturally, in the case of lithium, this is 2s band. Of course, this is formed by 2s orbitals, and since it is partially filled or half filled, this band also will be half filled. Okay, so lithium has a half filled 2s band, right? So like that, in a solid, all AOs of comparable, similar symmetry and size, energy will undergo LCA and form so many bands, right? And in the band, some will be filled and some will be empty. So in general, if we show, the band model of a solid will be like this. That is, okay, in the case of lithium, again let us take, lithium will have, of course, 1s band, which will be in the inner shell, and it will be very tightly held to the nucleus. So this is 1s band which will be fully filled because it is 1s2. So 1s band also will be fully filled. Above that there will be a wider, which is wider because it is the outer shell, electrons are loosely held. So the 2s band, what about 2s band? Since it is 2s1, 2s band will be half filled, right? It is half filled. So this is 2s band and it is half filled. So since it is half filled, electron can move here. So that leads to conduction. Now if we write, we can show it is 2p band is there because it is of course empty, no electrons. So like that there will be so many bands. Generally writing for a solid, there will be so many bands and we can classify the bands like this. See, let me show the band. Suppose this is one band, say 1s band, this is another band, 2s band, then 2p, 3s like that suppose. And this is fully filled band. Suppose this is also fully filled band. This is also filled band. Suppose it is like this. We have a few important terms here. This is called valence band, VB. VB means valence band. What is valence band? Fully filled, highest occupied band. Highest occupied band is called valence band, and this is called conduction band. That is the lowest unoccupied band. That is called conduction band. Why we call like this? Because when electron move from this valence band to conduction band leads to conduction. Now this gap here, the energy gap between valence band and conduction band is written as Eg, that is called energy gap. It's also called forbidden gap. Means electron cannot be anywhere here. That is not a permissible energy. So energy gap between valence band and conduction band is called energy gap. Okay. Now based on this energy gap, we can divide solids into three types. So based on band theory, the difference between conductor, semiconductor, insulator is like this. In the case of an insulator, the energy gap will be very large. See, suppose this is the conduction band. You have a very large energy gap. So electron cannot cross this energy gap to reach valence band and no conduction. So insulator is having very large energy gap, much above, roughly speaking, 3 electron volt. More than 3 electron volt energy gap. It's a rough estimate. In the case of a conductor, energy gap is sometimes 0. There are two possibilities. Sometimes it is that, as in the case of lithium, for example, the case of lithium is that this is 1s band, and what about 2s? It is partially filled, right? So in this case, there is no, since it is partially filled, electron can move within this band itself, so leads to conduction. So partially filled band can lead to conduction in conductor. Another possibility is that in the case of sodium or magnesium, etc., what happens is that the 2s band and 2p band is overlapping of bands. Conduction band is overlapping with valence band and no energy gap. So it can be either no energy gap or it can be a partially filled band leads to conduction. So conduction is possible here. Here also conduction is possible. Electron can move here. So conduction is possible. This is how conductors having either partially filled band or overlapping bands leading to conduction. Sodium, magnesium, lithium, tin, lead, etc. Coming to semiconductors, that is important for our discussion. In the case of semiconductor, it is in between. Here energy gap is very large, here it is negligible, and here energy gap is small. Suppose this is a conduction band and this is the valence band, sorry, this is a conduction band, and this is the valence band. Energy gap is small here. So the speciality of semiconductor is that they are having small energy gap. Sometimes it is 1 to 2 electron volt. Silicon, germanium are well-known semiconductors, and you know the importance of semiconductor industry in this era. And in addition to silicon, germanium, you know, they come in carbon family. Valency is 4, silicon, germanium. And see, these compounds are the neutrons. Instead of using silicon, germanium, we can make use of these compounds, which are called 13-15 compounds. What is the specialty? Gallium comes in group 30, arsenic comes in group 15. So 13 plus 15 is an average of 14. So these are having an average valence of 4, and they are having similar crystalline structure like that of silicon, germanium, and they show unusual semiconductor property. Zinc sulfide is a 12-16 compound, group 12, and sulfur in group 16, average of 14. So these are also used as semiconductors. Even as we discussed in the previous class, in defects in solids, there are certain crystalline solids which are having defects and having cation vacancy, like in FeO or nickel oxide, etc. They are having cation vacancy which can act as holes, electron deficiency, to which electrons can move and from neighboring bonds, and it can lead to conduction. So there are so many types of semiconductors. Now coming to the next one, that's very important, that is, what are the types of semiconductors? How we classify semiconductors, right? That is given here. Semiconductors are of two types. One is intrinsic or pure semiconductor, that is what we discussed here. That is pure semiconductor. So in the case of a pure semiconductor, or it is undoped, means no impurities added. We have just seen that in a semiconductor, it is that there is a small energy gap between the valence band and conduction band. Okay. So this is filled band, and this is empty, and energy gap is small. So let us see how conductivity takes place in a intrinsic semiconductor, that means silicon or germanium. Example is silicon, germanium, etc. That's pure semiconductor. How do they conduct electricity? This is the energy level diagram. So is the energy. This is the valence band, right? And this is the conduction band. And we have a small energy gap. Suppose this is small. So what happens? When you increase temperature, we know that conductivity of a semiconductor increases with rising temperature. So when temperature increases, what happens? Some electrons can move into the conduction band, right? That's called thermal electrons, thermally excited electrons. So the situation now is like this. When some electrons have gone up into conduction band, crossing this small energy gap, here comes certain vacancies. We can put it plus. Plus means holes, electron deficiency, because electron has lost, has moved, and here there will be electrons reach here, electrons here, right? So this is the case. Now these electrons can move in the conduction band, facilitating conduction. And also, since there are electrons down here in the filled band here, and there is some vacancy here, electron can break the covalent bonds and move to these holes, right? Neutralizing this hole, and hole appear down. That means electrons move in this direction here also. So that is how conductivity takes place in intrinsic semiconductor. But the problem is that increasing conductivity by rising temperature is not advisable, and it has limitation. So how to increase the conductivity of a semiconductor dramatically? That's the question. For that, there we've discussed what is called extrinsic semiconductor or doped semiconductor. What is doping? Adding small amount of impurity atoms into the semiconductor lattice. So, based on the type of impurity added, there are two types of extrinsic semiconductor, N-type and P-type. In N-type, we are adding group 15 elements. Group 15 elements like phosphorus, arsenic, antimony, bismuth. These atoms can be added to get N-type. N indicate negative, P indicate positive. In P-type semiconductor, we are adding group 13 impurity atoms like boron, aluminium, etc. Let's see how this increases the conductivity and what is the difference, right? Let me show the lattice of silicon or germanium. For example, we are showing a few of them. Right? So this is the lattice of suppose silicon, and we have added only a few amount of impurities needed for doping. Suppose we are adding phosphorus, and so some dopant atoms are occurring occasionally here and there in the lattice. So one phosphorus comes here. So what happens now? Then we know silicon has tetravalent like carbon. It will form 4 bonds tetrahedrally around it. So there will be, these are the bonds. Okay. Now phosphorus, you know, it is group 15 and having 5 valence electrons. So it will make use of its 4 electrons to form bond with silicon around, and there is 1 electron excess. There is an excess electron with phosphorus. So wherever phosphorus comes, there will be a free electron. And the electrons are negative, that's why we call N-type semiconductor. So this N-type semiconductor, this conduction is due to the free electrons associated with these dopant atoms. Now this phenomena can be explained according to band model. How we explain is like this. We know that there is a conduction band, filled valence band is there, and there is an empty conduction band, and there is a small energy gap, we know, right? This is valence band, this is conduction band, and this is energy gap. So what happens, you know, when you add a group 15 impurity, there will be a good amount of free electrons present in the lattice, and these electrons will now make up a new band that is called a donor band, or a new donor level. So this is a new donor level. A donor level is produced here due to these free electrons, right? So this contains the free electrons, and what happens is that now the energy gap is only this one. Energy gap is reduced to much, very small energy gap. So electrons in this donor level can easily go into this conduction band. Now this is energy gap, so conductivity will remarkably increase, right? So conductivity is possible. That's how conductivity takes place in N-type. Now coming to P-type, here group 13 elements are added. What about group 13? They are having only 3 valence electrons. So what happens is that I can show it here itself. I am changing it here. Now the impurity is, let's say it is boron, for example. Boron is added to silicon lattice. So what about the electronic structure now? Boron is having only 3 electrons. So when here there will be deficiency of 1 electron, right? This is the electron of silicon. Boron is having 3 electrons used for forming 3 bonds. And now there is an electron deficiency which appears as a hole. So there will be so many holes in the associated with the occasionally occurring dopant atoms, and these holes facilitate conduction because a covalent bond nearby can break and electron can move to this hole and hole appear here, and that can continue. So due to the presence of these holes, conductivity takes place. According to band model, how it comes, see, this is the valence band, filled valence band, and this is the empty conduction band, right? Valence band and conduction band. And what happens here? These holes or electron deficiency will generate or create a new acceptor level just above valence bands. So now it is like this, the acceptor level. So this is the, whereas here it is donor level, a new acceptor level is formed just above valence band, making energy gap very small, because electron in valence band can now easily move into this acceptor level which contain holes. So when electron goes here, what happens? That get neutralized and holes appear now here. Now electron can move within the valence band. So this is how p-type semiconductor works. Since it is electron deficiency or holes are responsible for conduction basically, which is positive, that's why it is called p-type semiconductor. Okay, so that's all about types of semiconductors. Thank you.